A blade of grass cannot slip between the stones of the Great Pyramid. That level of precision was achieved without lasers or computers. This video explores 25 ancient engineering methods that reveal a forgotten mastery of construction. You will gain a new understanding of human ingenuity that could actually solve modern architectural challenges. How did Roman concrete grow stronger in seawater for 2,000 years? What secret allowed Inca walls to dance through earthquakes without collapsing? By the end, your perspective on history and human capability will be fundamentally reshaped. We often assume our technology makes us superior, but what if the ancients knew something profound that we have simply forgotten? That precision began with a single block of granite. In the searing heat of an Egyptian quarry, workers faced a seemingly impossible task. They needed to slice through some of the hardest stone on earth, but their strongest metal was soft copper. Their solution was a lesson in patience and profound observation. They realized the sand beneath their feet, rich in quartz, was actually harder than the copper of their saws. By mixing this sand with water to create a gritty slurry and dragging a copper blade back and forth, they turned the sand itself into countless microscopic cutting teeth. This method, called abrasive sawing, did not cut the stone in the way we think of cutting. It ground it down grain by tiny grain over days or weeks. The result was not a rough hack, but an astonishingly flat surface. The joints between these multi-ton blocks were often so tight that, as you heard, not even a blade of grass could find its way through. This wasn't just about making things fit. That microscopic precision was the secret to their longevity. When an earthquake shook the ground, these perfectly mated stones could slide and settle as a single monolithic unit rather than cracking apart. Experts like engineer Mark Lehner have shown another facet of this stone wisdom. For shaping curves and hollows, workers used even harder dolerite stones as pounding tools, patiently tapping the granite into form through a relentless, rhythmic understanding of its crystalline structure. This reveals a fundamental truth about their engineering. It was never about dominating the material with superior force. It was a collaboration with the material, a deep knowledge of geology and friction applied with immense patience. In our world of diamond-tipped saws and instant results, what could we learn from that kind of deliberate, material-focused mastery? This foundational skill with stone empowered them to think bigger, leading to a logistical puzzle that defies belief. That patient understanding of stone laid the groundwork for an empire built to last. But what happens when you need to build not just on land, but within the sea itself? The Roman harbor at Caesarea presents a silent, stunning mystery. Its concrete breakwaters have been pounded by Mediterranean waves for 2,000 years, yet they stand firm, while modern concrete structures in similar saltwater environments often show significant wear in just a few decades. The difference was not in the scale of their ambition, but in the very chemistry of their mortar. The Romans engineered a material that defied time, and its secret was a volcanic ash called pozzolana. This was no ordinary ingredient. When mixed with lime and, crucially, seawater, it triggered a long-term chemical reaction that modern scientists are only now fully appreciating. Researchers like geologist Marie Jackson have studied samples of this ancient concrete, finding that the saltwater actually catalyzes the growth of rare, interlocking minerals within the material. These minerals, such as a form of aluminum tobamorite, act like a reinforcing crystalline skeleton, making the concrete grow denser and stronger over centuries, not weaker. This was active, intentional material science. They weren't just using what they found, they were creating a new substance with specific, visionary properties. This pozzolanic concrete was the enabling technology for an empire. It allowed for the construction of the vast network of aqueducts that brought fresh water to cities. It was the key to the Pantheon's magnificent, unsupported dome, and it built the roads, bridges, and ports that bound the distant provinces together. It was the physical backbone of Roman civilization. Their recipe was so effective that when the Western Roman Empire eventually declined, the precise knowledge of this concrete mix was lost for over a millennium. We are only now, with advanced microscopes and chemical analysis, beginning to reverse engineer their forgotten mastery. It forces a humbling question. If we lost such a transformative building technology once, what other material sciences perfected by ancient hands might still be waiting in the ruins for us to rediscover? This Roman genius for manipulating the physical world found its most vital expression not in monuments, but in the lifeblood of any civilization: water. The Roman aqueduct was a triumph of hydraulic will, but it was a rigid system. It could not bend. In the Andes, however, the builders faced a force that demanded not rigidity, but a brilliant, calculated flexibility. The ground itself could come alive with violent tremors. The Inca response was not to fight this force with immovable mass, but to design structures that could dance with it. Their mortarless stone walls, like those at Machu Picchu, are a masterclass in seismic intelligence. Each massive block was not a simple rectangle. It was a uniquely shaped trapezoidal piece in a three-dimensional stone puzzle. The sides were cut with a slight inward lean, and the joints between them were complex, interlocking faces. When an earthquake struck, these walls did not behave as a single, brittle unit. The precisely fitted stones would sway, the energy of the tremor traveling through the network of tiny contact points. They would shift and slide against one another, dissipating that destructive force through friction and movement. Then, as the shaking subsided, gravity would gently guide each stone back to its original resting place. It was a self-centering system, engineered centuries before the term existed. Modern seismic engineers study these walls with a sense of profound respect. The Inca, through meticulous observation and empirical trial, achieved what we now strive for with advanced computer models: a deep understanding of dynamics and load distribution. They built a conversation between stone and earth, allowing one to move without destroying the other. In a world where we often build to resist nature with sheer strength, the Inca philosophy offers a powerful alternative: to design with nature, to absorb and redirect its energy. This resilient architecture was never an isolated feat. It was the physical manifestation of a civilization that understood its environment intimately, a wisdom that extended from the foundations of their buildings to the very layout of their sacred cities. The arch is a shape of profound deception. It looks fragile, a curved gap in a solid wall, yet it possesses a hidden strength that transformed what buildings could be. This secret was first unlocked not with stone but with mud. In the river valleys of Mesopotamia, where great trees for timber were scarce, builders turned to the earth beneath their feet, forming countless bricks from clay and straw. Their great challenge was the doorway. A simple horizontal beam or lintel across an opening could only span a short distance before it would crack under the weight of the wall above. The Mesopotamian solution was a geometric revolution. They began molding their bricks into a new shape, a wedge. By arranging these tapered bricks in a semicircle, they created a structure that worked on an entirely different principle. The weight from above was no longer a downward force begging to snap a beam. Instead, it was converted, channeled along the curve of the arch, and pushed outward and downward along its sides into the supporting columns or walls. Each brick in the arch became a keystone, locking its neighbors in place through compression, making the entire form stronger under load. This was the birth of true architectural space. Suddenly, walls could have grand, stable openings. This innovation flowered into the magnificent Ishtar Gate of Babylon, its arched passageway adorned with glazed blue bricks and reliefs of dragons and bulls, a statement of power and divine connection. But the builders did not stop there. By extending the principle of the arch in one direction, they created the barrel vault, a continuous tunnel of masonry that could roof a long corridor or hall. This was the key to larger, more enclosed interior spaces, moving beyond the limitations of simple post and beam construction. The genius was in the distribution of force. The arch and vault managed weight so efficiently that it enabled more ambitious civic structures, temples, and palaces, all from humble, sun-baked bricks. This fundamental principle, conceived along the Tigris and Euphrates, would travel across continents and millennia. The Romans would later refine it with concrete and stone, building the aqueducts and colossal arenas we still marvel at today. Every stone bridge, every cathedral ceiling, every subway tunnel in our modern world whispers the legacy of those Mesopotamian engineers. Their innovation answers a deeper question about human progress. It wasn't about finding the strongest material, but about discovering the smartest shape. They taught us that true strength in construction often lies not in resisting force head-on, but in redirecting it, in guiding it along a path of our own intelligent design. This mastery over form and force would find another, more delicate expression in a place where the environment demanded not just strength, but a perfect, silent balance. A wooden pagoda sways gently in a storm, its tiers moving not as one rigid block, but like a supple tree bending in the wind. This was the genius of ancient Chinese carpentry, a system of construction that embraced movement as a source of strength. In a land prone to powerful tremors, builders turned to the most abundant material, wood, and devised a way to make it dance. The secret lay in the joints. Instead of nails or metal fasteners which would rust and create rigid, brittle points of failure, they perfected an art of intricate wooden joinery. Techniques like the mortise and tenon, a knob on one beam fitting perfectly into a socket on another, and the dovetail with its interlocking fan-shaped tails and pins, created connections that were firm yet forgiving. These joints allowed the entire timber frame to flex and shudder during an earthquake, absorbing the destructive energy through countless points of friction and slight movement. The crowning achievement of this philosophy was the dugong bracket set, appearing like a complex cluster of wooden clouds beneath the eaves of a temple roof. The dugong was far more than decoration. It was a sophisticated, multi-layered shock absorber. Each bracket was an independent unit of interlocking arms and blocks, stacked in a pyramid that transferred the immense weight of the heavy tiled roof down through the wooden columns. When force was applied from any direction, the individual pieces within the dugong could shift minutely, compressing and dispersing the energy before it reached the main structural frame. This system gave the building a remarkable ability to self-correct, swaying, and then settling back into alignment. The proof of its resilience stands in places like Japan's Horyuji Temple, a structure built with these Chinese techniques that has survived over 1,300 years of tremors and typhoons. Modern structural engineers and architects now look to these ancient wooden systems for inspiration in designing flexible skyscrapers and damping systems that can withstand seismic activity. The lesson is profound. While Roman concrete fought the sea with chemical permanence and Inca stone danced with the earth through friction, Chinese joinery created a dialogue with the forces of nature. It asked a fundamental question we are still learning to answer fully. How does building with a material's natural tendency to move and flex, rather than rigidly resisting that movement, create architecture that is not just strong but truly alive and resilient? This wooden mastery did not exist in isolation, but was part of a broader engineering vision that understood balance in all things. A vision that would soon confront one of humanity's most persistent and dangerous adversaries. A wooden pagoda sways, but a marble column must be lifted. The ancient Greeks confronted this immense physical challenge with a weapon far more powerful than muscle alone, the lever of the mind. While cultures mastered materials and forms, Greek thinkers like Archimedes formalized the principles that governed force itself, transforming abstract physics into the most practical of construction tools. Their genius was not merely in building, but in understanding why building worked and then amplifying that knowledge. Archimedes famously declared that with a lever long enough and a place to stand, he could move the world. This was not empty boasting, but a statement of profound mechanical truth. In the quarries and on the Acropolis, this principle took tangible form. A simple lever became a way to pivot multi-ton stone blocks onto sledges. A winch, essentially a rotating lever, could wind a rope with a force multiplied by the length of its handles. But the true masterpiece of amplification was the compound pulley system. Imagine a single rope threaded through not one, but a series of grooved wheels or sheaves mounted in a block. With each additional sheave, the force required to lift a weight is halved. A system with 5 sheaves could allow a team of 10 workers to lift what would normally demand the raw strength of over 300. This was the silent engine behind the Parthenon's construction. It was not an anonymous mass of laborers straining beneath a block, but a smaller, coordinated crew operating a sophisticated machine of wood and rope, guiding massive marble drums and lintels into precise position with controlled, manageable effort. This represents a pivotal shift in the story of engineering. It marks the moment where human ingenuity stopped trying to simply match nature's scale with more manpower and began to outwit it with mechanical advantage. The pulley, the lever, the winch, these were tools that made the builder's mind the strongest element on the site. The legacy of this intellectual approach is all around us. Every crane on a modern skyline, every hydraulic jack lifting a bridge, every gear in a complex machine is a descendant of that fundamental Greek insight. The physics they described remains unchanged, the true and permanent engine of all engineering progress. It answers a timeless question: how does humanity achieve the monumental? Not always by growing stronger, but by growing smarter, by discovering the hidden ratios and principles that allow a modest force to perform a Herculean task. This intellectual mastery over force would soon be directed toward a challenge of a different scale, not lifting stone, but commanding the very flow of water across an entire landscape. A lever moves a stone, but a civilization needs to move a river. In the vast, arid plateaus of ancient Persia, survival depended not on conquering the landscape, but on listening to its hidden whispers. The solution was not a grand aqueduct marching across the horizon, but a secret, subterranean river engineered in total darkness. The Persian Qanat is a masterpiece of invisible architecture. From the air, it reveals itself only as a line of craters, like a trail of gentle dimples stretching from a distant mountain foothill to a parched valley or a waiting city. Each of those craters is a vertical shaft, a breathing hole for a hidden canal that flows silently beneath the desert floor. This was engineering in reverse. Instead of bringing water to the people across the surface, the Persian engineers brought themselves down to the water. They began at the destination, a settlement in need, and carefully tunneled backward toward the distant source. Their primary tool was a profound understanding of gravity and geology. The tunnel had to have a perfectly calculated, gentle slope, just enough for the water to flow steadily, but not so steep that it would erode the channel or arrive with destructive force. Maintaining this gradient over distances that could span 50 kilometers or more, using only simple sighting tools and generations of accumulated knowledge, is a surveying achievement that still stuns modern engineers. The vertical shafts, sometimes numbering in the hundreds for a single Qanat, served a triple purpose. They provided air for the diggers working deep underground. They were the chutes for removing excavated earth, and once the system was complete, they became vital maintenance access points. The brilliance of the design was in its profound sustainability. By burying the water channel, the engineers solved two of the desert's greatest threats: evaporation under the blistering sun, and contamination from sand and debris. The Qanat delivered cool, clean water directly to where it was needed, creating lush garden oases in the midst of barren plains. These systems became the literal lifeblood of empires, enabling agriculture, supporting cities like ancient Persepolis, and fostering community, as the shared responsibility for maintaining the Qanat bound people together. The most remarkable fact is that many of these ancient waterways, some over 3,000 years old, are still in use today, a testament to their flawless, passive design. In an age where we often tackle resource challenges with massive, energy-intensive pumps and treatment plants, the Qanat asks us a quiet, powerful question. What if the most advanced solution is not to overpower our environment, but to work with its hidden logic, to create systems so elegantly tuned to natural laws that they endure for millennia without a single watt of electricity? This was not just irrigation, it was a philosophy of harmony carved into the earth itself, a lesson in patience and precision that would find a startling parallel in a very different form of ancient calculation. A hidden river flows beneath the desert, but a silent giant must walk across an island. The Moai of Easter Island stand with their backs to the sea, gazing inland, but their journey began in a distant quarry. Each multi-ton statue presented a problem of almost mythical scale. How does a community with no wheels, no draft animals, and no metal transport a stone colossus for miles across rolling terrain? The answer lies not in magic, but in a profound, practical mastery of friction and force. Evidence points to a combination of ingenious, low-tech solutions. One method likely used a sledge, a wooden platform upon which the statue was secured. But the true innovation was what lay beneath it. Logs were laid perpendicular to the direction of travel, creating a temporary track. As the sledge was pulled forward, teams behind would rush the now freed rear logs to the front, creating a continuous, rolling pathway. This simple system of wooden rollers transformed sliding friction, which is high and stubborn, into rolling friction, a far weaker force that could be overcome by a coordinated team with ropes. Some researchers propose an even more dynamic method for the final, upright moai, a walking technique. By attaching ropes high on the statue and rocking it side to side with rhythmic pulls, teams could have literally walked the giant forward in a careful, swaying gait, using its own rounded base as a pivot. Modern experiments have proven the stunning efficiency of these ideas. A group of just 18 people, using ropes and a system of rocking, successfully moved a full-scale concrete replica moai hundreds of meters. The achievement was not in the complexity of the tools, but in the sophistication of the plan. This was logistics engineering on a monumental scale. It required precise coordination, a shared rhythm, and an iterative understanding of physics learned through direct, hands-on experience. They were not just moving stone, they were conducting a symphony of human effort, where timing and teamwork were as crucial as strength. The same principles echo at Stonehenge, where the massive sarsen stones were likely transported on sledges greased with animal fat, sliding over a prepared track of timber rails. These methods reveal a universal ancient truth. The most staggering results often come not from a single revolutionary invention, but from the brilliant collective application of the simplest mechanical principles: leverage, reduced friction, and distributed weight. It answers a silent question posed by every megalith. How does humanity move the immovable? By turning the problem into a process, by breaking the impossible journey down into 1,000 manageable pulls and rolls, guided by a shared vision. Yet, moving a stone to its destination is only half the miracle. The greater puzzle begins when it finally arrives and must be coaxed from its horizontal journey into a permanent, vertical silence. A statue stands upright only when its journey is complete, but a bridge must hold its form while suspended over a rushing void. The Romans solved this paradox of mid-air construction with a brilliant, temporary lie. They built a false structure to hold the truth of the bridge until the bridge itself could remember how to stand. Look at the Alcantara Bridge in Spain. Its 6 monumental arches of granite leaping across the deep gorge of the Tagus River. It has done so for nearly 2,000 years, surviving wars, floods, and the relentless wear of time. Its endurance is a testament not just to the strength of the arch, but to the ingenious process that allowed such a span to be born. The Romans had perfected the semicircular arch, understanding its compressive strength, but building one over a deep river presented an impossible chicken and egg problem. The arch's stones, called voussoirs, rely on each other for support in a completed ring. Yet, during construction, with the ring incomplete, they have nothing to push against and would simply tumble into the water below. The Roman solution was the centering, a massive, curved wooden framework built out from the piers. This temporary scaffold held each precisely carved stone in its exact position, bearing the entire weight of the half-built arch. It was an act of profound faith in geometry and craftsmanship. Only when the final, wedge-shaped keystone was tapped into place at the very crown of the arch did the magic happen. The completed stone ring suddenly became a single, coherent structure. The weight that had been borne by the wooden centering was instantly transferred, flowing down through the curve of the stones and into the sturdy piers. At that moment, the temporary wooden skeleton became useless. It could be removed, and the arch would stand, finally self-aware of its own strength. This technique allowed Roman engineers to span wider, deeper rivers than ever before, with a stability that feels eternal. They complemented this with other subtle masterstrokes. They used a special, waterproof cement in the submerged piers to protect them from being scoured away by the current, and they often shaped the piers themselves with angled cutwaters upstream to slice the flow of the river, reducing pressure during floods. These bridges were far more than crossings. They were the critical, unbreakable knots in the vast net of Roman roads, the Via Appia and all the others. They enabled the rapid movement of legions that secured the empire and the steady flow of goods and ideas that enriched it. They were instruments of unity, turning geographical obstacles into connective tissue. The principle of temporary support remains absolutely fundamental in modern engineering. Every concrete bridge or building floor built today uses formwork, a direct descendant of Roman centering. We still build the temporary lie to realize the permanent truth. This method answers a quiet question at the heart of all great construction. How do you build the future when the present cannot yet support it? You build a scaffold of trust in the final form, a temporary structure of wood and will that holds the vision in place until the stones themselves learn to hold each other. The arch remembers how to stand, but water must be taught how to wait. In the arid plains of India, the answer was not to build up, but to carve down, creating a cathedral in reverse. The Stepwell of Chand Baori is a staggering geometry of survival, a colossal, inverted pyramid with over 3,500 precise steps descending 13 stories into the Earth's cool embrace. This was not merely a hole in the ground. It was a masterclass in hydrological engineering and stone craftsmanship, a machine for living with drought. Its design was a direct conversation with the monsoon. During the brief, intense rains, the vast, terraced catchment area would funnel every precious drop into the deep central reservoir. Then, as the long dry season parched the land above, the community would descend the labyrinthine staircases to access the steadily receding water. The architecture was perfectly tuned to this fluctuation. Each step, each platform was a calibrated marker of the water table, allowing access even as the level dropped dozens of meters. The engineering brilliance is in what you do not see. The staggering weight of all that excavated earth pushing in on the walls was counteracted by the stepwell's own form. The cascading terraces and staggered staircases acted as a series of internal buttresses, distributing the immense lateral pressure and preventing collapse. This created a space that was astonishingly stable, silent, and cool, a natural refuge from the desert heat. But the true mastery of the Stepwell was its holistic vision. It was never just a reservoir. It was a subterranean community center, a place for ritual, for social gathering, and for quiet respite. Ornate pavilions, carved niches, and shaded galleries lined the descent, transforming a utilitarian necessity into a profound architectural and social experience. Utility, beauty, and community were woven into a single, seamless design. In our modern era of hidden pipes and sterile treatment plants, the Stepwell asks a poignant question. What have we lost by separating the function of water management from the human experience? These structures celebrated water as the center of communal life, making its conservation and use a visible, shared, and even sacred responsibility. This integration of the practical and the spiritual points toward a deeper layer of ancient thought, where the very shapes of their constructions were believed to hold a power beyond the physical, guided by a silent, mathematical order. The silent order of a stepwell is a geometry carved into the earth, but a city demands a different kind of order, one written across the open landscape. Walk the streets of ancient Priene in modern-day Turkey, and you are walking a blueprint for civilization itself. Its precise grid of straight, intersecting streets feels startlingly modern, a stark contrast to the organic, winding paths of older settlements. This was the Hippodamian plan, a revolutionary idea attributed to the thinker Hippodamus of Miletus in the 5th century before the Common Era. It was more than just a street map. It was a philosophical statement about how humans should live together. The plan divided the city into uniform, rectangular blocks, each with a designated purpose. Public spaces like the agora for commerce and debate, the theater for performance, and sacred temples were given pride of place, while private housing occupied standardized plots. This rational division optimized space, ensured equitable access to sunlight and air, and critically, facilitated advanced drainage and sewage systems that flowed predictably along the graded streets. The grid was a tool for efficiency, defense, and public health, allowing for the rapid movement of people, goods, and, if necessary, soldiers. It represented a shift from a city that simply grew to a city that was designed, from a collection of buildings to a functioning social organism. The Romans, masters of systematization, adopted and expanded this principle across their vast empire. In new colonial towns from Britain to North Africa, they imposed a template centered on two main, perpendicular arteries, the Cardo running north-south and the Decumanus running east-west. This cross divided the city into 4 quarters with the Forum, the civic heart, placed at their intersection. This was urban planning as an instrument of empire, a way to instantly impose Roman identity, control, and logistical efficiency on any terrain. The straight, wide roads were not just for parade, they were for supply lines, communication, and the projection of power. The legacy of this ancient order is literally beneath our feet in cities from New York to Barcelona. The gridiron street plan is the unseen skeleton of the modern metropolis, enabling address systems, utility grids, and public transit. It answers a fundamental question about human society. How do we create a shared space that is both functional and fair? The Hippodamian and Roman planners believed the answer lay in rational, repeatable geometry, in creating a framework so logical it could foster community, commerce, and health for generations. This commitment to a strong, organized foundation, however, was not limited to the layout of streets. It extended down to the very first layer of every important structure they built. A hidden world of preparation that determined whether a building would stand for decades or for millennia. A grid of streets organizes a city, but a tomb must hold a mountain of earth. In the shadowed hills of ancient Mycenae, engineers faced this very challenge, and their solution was a slow, patient miracle of stacking. The so-called treasury of Atreus is not a vault in the Roman sense. It is a soaring, beehive-shaped chamber built entirely without arches, using a method as simple as it is daring, the Corbelled vault. Picture a room where the walls do not stop at the ceiling line, but simply begin to lean inward, each massive stone block placed so its inner edge hangs slightly over the one below. Layer by careful layer, the circle of the wall grows smaller, the stones reaching across the growing void until at the very top, a single capstone closes the eye of the dome. This was architecture as a high-stakes balancing act, a conversation with gravity itself. The Mycenaean builders were not distributing force along a graceful curve like a true arch. Instead, they were counteracting it through sheer mass and meticulous offset. Each stone had to be placed with perfect calculation, its center of gravity kept firmly over the stone beneath it. A single misaligned block could create a point of weakness, a lever that might cause the entire inverted cone to unravel under the immense weight of the earth mound heaped above it. That they succeeded on such a monumental scale, creating a space over 43 feet high and wide, speaks to an empirical, hands-on mastery of statics learned through generations of trial and observation. The Corbelled vault was not the most efficient way to span a space. It required enormously thick walls, but it was a brilliant answer to the materials and knowledge they possessed. It allowed them to create grand, uninterrupted interior chambers without needing vast timber beams, which were scarce, or understanding the compressive magic of the arch, which was still centuries in the future. This beehive tomb stands as a testament to the power of incremental innovation. It represents a crucial stepping stone in humanity's architectural imagination. Before the elegant solution exists, there is often a period of robust, ingenious workarounds. The Mycenaeans proved that by patiently stacking stone upon stone, by daring to let each layer reach a little further into the empty air, they could literally build a mountain of space from the ground up. Their Corbelled vaults would echo through history, influencing later underground constructions and serving as a profound lesson. Sometimes, the path to a revolutionary breakthrough is paved not by a single flash of genius, but by the persistent, iterative refinement of a simple, bold idea. This mastery of balancing mass against void, however, would find a far more delicate and precise expression in another part of the ancient world, where the challenge was not to support a mound of earth, but to capture the very movement of the heavens themselves. A beehive tomb balances weight through patient stacking, but a single shaft of stone must first be freed from the earth itself. In the royal quarries at Aswan, the unfinished obelisk lies like a sleeping giant, still partly attached to the bedrock of pink granite. It is a fossilized moment of ambition, revealing every step of an almost unimaginable process. This was not a sculpture carved from a delivered block. It was a skyscraper of stone conceived and birthed directly from the living earth. The first act was one of surgical separation. Workers would carve narrow channels in the rock, outlining the future obelisk on all four sides. Then, into these channels, they would drive dry wooden wedges. The real magic began when they poured water over the wood. The wedges would swell with tremendous, slow force, creating a clean, controlled fracture along the predefined lines, prying the multi-hundred-ton monolith free from its mother stone. It was a technique that used the natural properties of materials against each other, a patient dialogue with physics. Once liberated, the obelisk faced its second impossible journey, a voyage down the Nile. It was loaded onto a colossal, specially built barge, a vessel so large and so precious that, according to inscriptions, the pharaoh himself would come to witness its launch. The river current and careful piloting did the work of thousands of haulers, but the final act, the erection, was the most daring ballet of all. At the temple site, workers constructed a high earthen ramp leading to the edge of a prepared stone socket. The obelisk was dragged up this ramp, base first, until its lower end overhung the pit. Then, with ropes controlling its descent from multiple directions, teams began the meticulous work of excavating the sand from beneath the ramp. As the sand was removed, the obelisk's base would begin to sink into the socket. The angle changed with agonizing slowness, the monument pivoting downward, its towering tip rising against the sky in a slow, majestic arc. This was a moment of supreme tension. The coordination had to be flawless, too fast, and the stone would shatter on the socket's edge, too uneven, and it would topple. But when executed perfectly, gravity itself became the primary lifting force, gently lowering the base as it raised the tip, until the monolith stood perfectly vertical, a captured sunbeam of stone. The entire operation, from quarry to raising, was a masterclass in phased project management. Each stage was discrete, each risk calculated and mitigated with the technology at hand. The quarrying relied on controlled fracture. Transport leveraged the natural highway of the Nile. Erection used a temporary earth structure to convert a vertical lift into a controlled pivot. There were no second chances. This was engineering without a safety net, where planning, timing, and collective trust were the most vital materials. In our world of computer simulations and hydraulic cranes, what can we learn from such a high-stakes, sequential operation? It teaches that the most complex achievements are often a series of well-understood simple steps, executed with unwavering precision and a deep respect for natural forces. The obelisk was more than a monument, it was a declaration. It said that human will, when guided by patient intelligence, could make a mountain kneel and set a sliver of the earth's bones pointing directly at the sun. An obelisk points to the sun, but an empire runs on the ground beneath its feet. The famous Roman road was not a simple dirt track worn smooth by sandals. It was a layered, engineered landscape, a permanent incision into the earth designed to outlast the legions that built it. To create a via munita, a fortified way, began with a profound act of commitment. Engineers would dig a trench, the fossa, often 3 to 4 feet deep. This was not just for drainage, it was to reach stable, undisturbed ground, removing all soft, unreliable soil. Into this prepared wound, they began a meticulous 5-layer construction. First came the pavimentum, a leveling bed of sand or fine mortar. Upon this, they laid the stotumen, a foundation of large, fist-sized stones packed tightly for stability. Next was the heart of the road's strength, the rudus, a thick middle layer of smaller gravel and crushed stone bound together with lime mortar, creating a rigid, concrete-like platform. On top of this sat the nucleus, a finer mix of sand, lime, and pottery shards for final leveling. Finally, the visible surface, the summum dorsum, was paved with carefully fitted polygonal stones of hard basalt or granite. These top stones were not flat, they were slightly convex, cambered so that rainwater would run off into the drainage ditches that flanked every road. This was infrastructure built with a geological patience. Each layer had a specific purpose, from load distribution to water management, working in concert to create a surface that could bear the relentless pounding of army boots, supply wagons, and trade caravans for centuries. The famous straightness of these roads was a strategic choice, not just an aesthetic one. A straight line is the shortest distance, enabling the fastest possible movement of messengers, the famous cursus publicus, who could carry news from Rome to its farthest provinces in a matter of weeks. These roads were the physical internet of the ancient world, transmitting information, military power, and economic goods with an efficiency unmatched until the railway. They were instruments of control, yes, but also of unity. A merchant in Gaul and a farmer in Syria walked on the same engineered surface under the same system of law. The road was a tangible promise of Roman order. The legacy of this layered approach is everywhere in modern civil engineering. The foundational principle of a stable subgrade, followed by aggregate base layers and a durable wearing surface, is the direct descendant of Roman practice. It answers a timeless question about enduring systems. How do you build something that lasts, not with a single, heroic effort, but with patient, intelligent layering, where every component has a clear role in a unified, resilient whole? These stone veins carried the lifeblood of an empire, a flow of people and ideas that would eventually require not just paths to travel, but secure places to rest and exchange goods, leading to a different kind of architectural anchor in the landscape. A road's straight line is a promise of speed, but its accuracy begins with a single, silent observation. Before a single stone of the Great Pyramid could be laid, or the first mile of a Roman aqueduct plotted, ancient engineers faced a foundational challenge: how to translate a grand vision from the mind's eye into the stubborn reality of the landscape. Their tools were breathtakingly simple, yet their results remained breathtakingly precise. The Roman groma, for instance, was little more than a vertical staff with a cross of arms from which plumb bobs hung on strings. By sighting along these perfectly vertical lines, a surveyor could establish flawless right angles, the essential geometry for laying out city grids, military camps, and building foundations. For leveling over long distances, they turned to the inherent wisdom of water. A simple water level, a length of hose or two connected vessels, exploits a fundamental law: water always seeks its own level. By observing the water line at each end of the device, workers could ensure that an aqueduct channel maintained its crucial, gentle downhill slope across miles of undulating terrain, a feat vital for a constant flow. The Greek dioptra was more sophisticated, a sighting tube mounted on a calibrated circular plate, acting as an early theodolite for measuring both horizontal and vertical angles. This allowed for precise alignment over long visual baselines, such as tunneling through a mountain from both sides to meet in the middle, but perhaps the most profound alignments were celestial. The Great Pyramid of Giza is oriented to the cardinal directions with an error of less than 1/15 of a degree. This was likely achieved by tracking the circular path of a star around the celestial pole, bisecting its arc to find true north. This was not mere symbolism, it was high-precision applied astronomy, linking the eternal order of the heavens to the temporal order of human construction. These methods reveal a profound truth: precision engineering has never been solely about the complexity of the tool, but about the clarity of the principle behind it. The plumb bob relies on gravity, the water level relies on fluid equilibrium, the star sighting relies on geometry. By mastering these immutable natural laws with simple, reliable instruments, ancient builders achieved an accuracy that still commands respect. In our age of GPS and laser levels, we risk divorcing ourselves from these fundamental principles. The question their work poses is vital. Could a deeper, hands-on understanding of basic geometry and natural forces, the very kind that guided a groma or a water level, lead to more resilient, more harmoniously integrated designs today? This mastery of measurement was the silent, essential first chapter in every story of ancient construction, the act of writing intention onto the earth itself before the first foundation stone ever touched the ground. The surveyor's line writes intention on the earth, but the architect's dream is to suspend heaven within walls. Gaze up into the great dome of the Hagia Sophia in Istanbul, and you are witnessing a geometric miracle. The dome does not simply rest upon the building, it appears to float on a ring of light streaming from its windows, defying the logic of weight and support. This illusion of celestial lightness was made possible by one of history's most elegant structural solutions, the Byzantine pendentive. Before this innovation, builders faced a stubborn geometric puzzle. How do you gracefully place a circular dome, the perfect symbol of the heavens, upon a square or rectangular base, the shape of the earthly realm? Earlier solutions were awkward. A circular drum could be built on a square base, but it created heavy, dark corners. The Romans used the squinch, a small arch built across each corner, but it created a fragmented, octagonal transition. The Byzantine architects of the 6th century sought something more unified, more soaring. Their answer was a piece of spherical geometry made solid. The pendentive is a curved, triangular segment of a sphere, like a concave, sculpted sail. 4 of these were placed in the upper corners of the square building. Each one rises from a single point at the bottom corner and curves upward and inward, meeting its neighbors to form a continuous circular rim at the top. This rim then became the perfect, stable base for the dome. The genius of the pendentive was not just in creating a circle from a square, but in how it managed force. The immense downward and outward thrust of the heavy masonry dome was captured by these curved triangular forms. The pendentives channeled that colossal weight smoothly, directing it down along their curves into the 4 massive piers at the building's corners. This transformed a problem of support into an act of fluid redirection. The entire interior space below was thus liberated. There were no thick walls or forest of columns interrupting the vast, unified volume. The eye could sweep uninterrupted from corner to corner, up into the dome itself, creating that breathtaking sense of boundless space that defines Byzantine sacred architecture. This was a revolutionary step beyond the Roman barrel vault. It was structural geometry as an artistic and spiritual statement. The pendentive made the impossible interior possible, a space that felt both intimately human and cosmically vast. Its influence radiated for centuries, shaping the great domed churches of Orthodox Christianity and later inspiring Renaissance architects in their own quests to marry circle and square. It answers a silent question posed by every ambitious builder. How do you solve a fundamental conflict of form, not by forcing one shape to conquer another, but by discovering a third, transitional geometry that makes them partners, transforming a structural necessity into the very source of awe? This mastery of form and light to shape human experience would find a parallel in a very different ancient tradition, one that sought not to capture heaven in a dome, but to harness the wind itself for pure, practical comfort. A dome floats on light, but a mountain of mud must defy gravity and time. In the flat, sun-baked river plains of Mesopotamia, where stone was a distant dream and timber scarce, builders created their own sacred mountains from the earth itself. The Ziggurat was a colossal staircase of mud bricks, a temple raised high to bring priests closer to the heavens. Yet mud brick is a humble, brittle material, prone to cracking under its own weight and vulnerable to the region's tremors. The Mesopotamian solution was a stroke of layered genius. Between each course of sun-dried bricks, workers laid down sheets of woven reed matting or networks of ropes. This was not just a leveling bed, it was a hidden tensile web. When the ground shook or the heavy structure settled, these flexible layers absorbed the stress, distributing it and preventing cracks from propagating through the brittle brickwork. They acted exactly like the steel rebar we embed in modern concrete, providing tensile strength to a material that is strong only in compression. This composite approach revealed a profound understanding of complementary properties. The brick resisted crushing weight, while the reeds resisted pulling and shearing forces. Together, they created a hybrid material far more resilient than either could be alone. Further protecting this earthen core was the use of bitumen, a naturally occurring tar collected from seeps in the earth. This thick, sticky substance served as a waterproof mortar and outer coating, shielding the vulnerable mud bricks from the rare but devastating downpours that could otherwise melt a city back into the plain. The entire construction was a meticulous layering of opposites, brittle with flexible, porous with impermeable, earth-bound with aspirational. These ziggurats, like the famous Etemenanki in Babylon, were more than architectural feats, they were conceptual bridges. They physically manifested a link between the fertile, human world below and the divine realm above, their stepped sides a literal and symbolic staircase. This ancient composite logic echoes powerfully in our world today. Fiberglass combines brittle glass strands with flexible resin, Reinforced concrete marries concrete's compressive strength with steel's tensile resistance. The principle is identical, combining dissimilar materials to cancel out each other's weaknesses and amplify their strengths. The Mesopotamian builders, working with reeds and mud, grasped this fundamental engineering truth millennia ago. Their work asks us a quiet, enduring question about our own constructions. Are we designing with materials, or are we designing with relationships, seeking those perfect partnerships between elements that create something entirely new, something capable of reaching for the sky while being rooted in the sober reality of the earth? A sacred mountain of mud stands firm, but a vessel must learn to dance upon the open ocean. The Norse longship was not built to resist the sea, but to become an extension of its rhythm, a masterpiece of flexible engineering. Its strength came from a method known as clinker construction, where the hull's planks were not laid edge to edge, but overlapped like the scales of a great fish. Each overlapping seam was fastened with iron rivets, creating a hull that was not a rigid shell, but a supple, articulated skin. When a massive wave struck, this hull could twist and flex, absorbing the immense energy rather than shattering against it. This was a fundamental rejection of brute force in favor of intelligent resilience. Beneath this flexible skin ran the ship's backbone, a deep, robust keel carved from a single, massive oak log. This keel served a dual purpose. It acted as a central spine, giving the longship structural integrity and preventing it from being pushed sideways by the wind, a principle known as lateral resistance. And it cut deep into the water, providing a fixed reference point that allowed the ship to hold a steady course across trackless seas, whether sailing close to the wind or running before a gale. The combination was brilliant, a flexible hull married to a rigid spine. This engineering demanded a profound, tactile knowledge. Shipwrights selected timber not just for size, but for its natural grain, shaping planks to follow the wood's inherent strength. They understood hydrodynamics through experience, carving the bow and stern into sleek, symmetrical lines that parted the water with minimal drag. Every joint, every rivet, was a calculated decision in a vessel that needed to be both lightweight enough to be carried across portages and strong enough to survive the North Atlantic's fury. The result was a machine of exploration, trade, and cultural connection that had no equal in its time. These ships reached North America, navigated the rivers of Russia, and raided coasts from Ireland to the Mediterranean. They were vehicles of transformation, and their design philosophy offers a powerful metaphor for all construction. What if we designed our static buildings not as immutable fortresses, but with a similar principle of calculated flexibility? Modern seismic base isolation systems, which allow a building's foundation to slide during an earthquake, are a direct echo of the longship's flexible hull. The lesson is clear: whether facing the force of waves or the force of tremors, sometimes the strongest response is not to stand unmoving, but to be designed to move, to adapt, and to remain intact through graceful compliance. The Viking shipwrights, in their intimate dialogue with wood and water, mastered a form of dynamic engineering that feels remarkably modern, proving that ancient innovation sailed on the horizon of every known sea. A flexible hull rides the waves, but a mountain can be taught to become a temple. In the quiet hills of western India, the Kailasa temple at Ellora presents a paradox that defies every instinct of construction. It is not a building that was raised from the ground up. It is a mountain that was meticulously, reverently carved from the top down. This is the ultimate act of subtractive architecture, where 300,000 tons of solid basalt cliff were not assembled but removed to reveal a sacred form sleeping within the stone. The process inverted all conventional logic. There were no bricks to lay, no blocks to hoist, no margin for error. Every strike of the hammer and chisel was permanent. A single misjudgment could shatter a delicate pillar or ruin a planned wall, with no possibility of patching or replacing the living rock. This demanded a kind of visionary foresight that is almost unimaginable. Before a single worker touched the cliff face, master architects must have held the complete three-dimensional temple in their minds, then translated that vision into a precise, phased excavation plan. Historians suggest they likely established vertical benchmarks and guiding trenches, mapping the grand silhouette of the temple complex onto the rock like a colossal, three-dimensional blueprint. Teams of sculptors then began their work, not as separate groups of diggers and decorators, but as a unified force. As they excavated downward, they were simultaneously carving the intricate details, the soaring pillars, the graceful statues, and the ornate roof panels from the very material they were clearing away. The rock was both the obstacle and the finished product. This method transforms our understanding of creation. Where most building is additive, a process of bringing disparate parts together, Kailasa was an act of revelation. It was the patient uncovering of something believed to be already present, a sacred geography hidden within the mountain. This philosophy speaks to a profound relationship between vision, planning, and execution. The vision had to be absolute and immovable, for the planning could not afford ambiguity, and the execution required the steady hands of artists who could see the final form in the raw stone as they worked. It was architecture as an act of supreme faith, not just in the divine, but in the unwavering clarity of the initial idea. In our modern projects, where we so often build through iteration and adjustment, Kailasa stands as a monumental testament to a different path. What does it mean to begin with such a complete and perfect vision that the entire years-long process is merely the careful removal of everything that is not that vision? It suggests that the most enduring creations may not be built but discovered, waiting within the raw potential of the material or the mind for a hand steady enough and a plan clear enough to set them free. The warmth of a Roman bathhouse was not a luxury. It was a calculated science woven into the very bones of the building. Beneath the polished marble floors where citizens gathered, an invisible furnace breathed life into the stones. This was the hypocaust, an ancient system of central heating that transformed architecture into a living climate control device. At its heart was a simple but brilliant principle: heat rises. Outside the bath complex, a dedicated stoker tended a perpetual fire in a furnace, the prefurnium. This furnace did not heat water directly. Instead, it superheated the air in a hollow space beneath the floor. This underground chamber was not an empty void, but a forest of short, sturdy brick pillars called pilli. These pillars supported the heavy floor slabs above while creating a continuous, open channel for the hot air to snake and swirl. From this subterranean oven, the heated air was then channeled upward through specially designed hollow tiles embedded within the walls themselves, called tubuli, before finally escaping through discrete flues in the roof. The entire building became a radiator, its floors and walls emitting a gentle, pervasive warmth that banished damp and chill. The engineering sophistication here is profound. The layout and height of the pilli had to be meticulously planned to ensure even support and optimal airflow, preventing hot spots or cold corners. Builders were intuitively managing thermodynamics, understanding that the system's efficiency depended on the careful balance of heat input, air volume, and exhaust. This was not just about comfort, it was a monumental advance in public health. By creating large, warm, dry public spaces, the hypocaust system made social bathing and communal gathering possible year-round, promoting hygiene and wellness in crowded urban centers. It turned the bathhouse into the heart of Roman social life, a place for conversation, business, and relaxation, all enabled by this hidden technological marvel. The question it leaves for modern design is strikingly relevant. In an age of energy-intensive forced air systems and electric heaters, what could we learn from integrating climate control so seamlessly into a building structure? The hypocaust reminds us that the most efficient comfort systems are often those that are passive, that use the building itself as the medium for temperature regulation. This Roman mastery of interior climate points toward a final, overarching theme in our exploration of ancient methods, a theme not of controlling the environment, but of listening to its most subtle and powerful language. The warmth of a hypocaust was a hidden science, but in the jungles of Central America, architecture itself was designed to speak. The Maya built temples that were not just monuments to see, but instruments to hear. To create the soaring interior spaces within their stone pyramids, they perfected a version of the corbelled vault, often called a false arch. They would raise two parallel walls, then gradually bring them closer together by having each new course of stone extend slightly inward over the one below, until the gap was finally bridged by a single capstone. This created a narrow, triangular vault, a stone canyon that channeled sound as deliberately as it channeled spiritual aspiration. But the true acoustic mastery lies outside, on the grand staircase of the Pyramid of Kukulkan at Chichen Itza. Stand at its base and clap your hands once. The echo that returns is not a simple repetition. It is a sharp, chirping sound, uncannily like the call of the sacred Quetzal bird, a creature deeply woven into Maya cosmology. This was no accident of stone. It was engineering as sacred symbolism, achieved through breathtaking precision. The sound of the clap travels up the steep staircase, striking each of the pyramid's 91 steps. The geometry of those steps, their uniform height and depth, acts like the teeth of a giant stone comb, breaking the single sound wave into a rapid series of reflections. These micro-echoes return to the listener's ear so quickly in succession that they blend into that distinctive avian chirp. The material of the stairs, the limestone itself, was chosen for its specific reflective properties. Every element, from the grand sweep of the design down to the texture of the stone, was part of a calculated acoustic formula. This reveals a layer of ancient engineering we often overlook: multi-sensory design. For the Maya, a building was not complete if it only pleased the eye. It had to engage the ear to literally resonate with the spiritual world. The pyramid was a calendar in stone, aligned with equinoxes to create a serpent of shadow, and it was also a temple that could converse with the gods through engineered sound. Their cosmology saw no separation between the physical and the metaphysical, between the vibration of a handclap and the voice of a sacred animal, between the alignment of a doorway and the path of Venus. Their construction was a unified whole, weaving astronomy, acoustics, and architecture into a single experiential tapestry. This challenges our modern, often siloed approach to design. We engineer structures for visual impact and structural soundness, but how often do we consciously engineer for sound, for echo, for the emotional resonance a space can generate through its auditory signature? The Maya remind us that the most profound environments are those that speak to all our senses, that a space remembered is often a space that made us listen, turning geometry into meaning and stone into song. A temple that sings is an instrument of the divine, but a theater must make the human voice immortal. In the sun-drenched hills of Epidaurus, a whisper defies distance. Sit in the highest tier of the ancient theater, over 55 meters from the circular orchestra floor, and you can hear a pin drop on the stage, or the delicate rustle of an actor's costume. This is not a legend, it is a reproducible acoustic miracle, achieved 2,400 years ago without a single microphone. The secret was not magic, but a profound, mathematical collaboration between form and physics. Every element of the theater's design was a calculated component in an acoustic amplifier carved from limestone. The stepped seating, the cavea, was not merely for visibility. Its precise, fan-shaped rows acted as a natural acoustic filter. The low-frequency rumble of the moving crowd, the shuffling and murmurs, was absorbed and dampened by the stone itself and the space between the spectators. Meanwhile, the higher frequency sounds of speech and song from the stage struck the rows at specific angles, reflecting cleanly upward in a cascade of clarity. The material choice was critical. The limestone of the seats had just the right porosity and density to reflect sound without creating a harsh echo. The orchestra's perfect circular shape played a role, creating a focal point that helped project sound evenly. Even the slope of the hillside into which the theater was built was part of the equation, providing a natural, vibration-free foundation. While modern acoustic engineers can model the principles, the precise harmonic formula the Greeks used, the exact ratios of step height to depth, the curvature of the seating, remains partly elusive, a testament to an empirical mastery learned through iterative design and deep listening. They understood sound wave propagation as a physical geometry they could shape in stone. This achievement transforms our understanding of the space. The theater was not a passive container for drama, it was an active participant. The audience did not just witness the performance, they were acoustically connected to it, each person a point in a vast human receiver that made the most subtle emotional inflection from the stage universally accessible. It was democracy made audible, where every citizen, regardless of seat, shared the same auditory experience. This raises a resonant question for our own era of digital amplification and sound systems. What profound knowledge of natural acoustics, of how shape and material conduct the human voice, have we sidelined in favor of electronic solutions? The theater at Epidaurus suggests that the most powerful amplification comes not from adding technology, but from perfecting the inherent resonance of space itself. It reminds us that in the quest for connection, sometimes the most advanced design is the one that disappears, leaving nothing between the speaker and the listener but perfectly guided air and intention. A whisper travels across stone, but a bridge must withstand a river's roar. In the heart of Hebei Province, China, the Jeju Bridge has done exactly that for over 1,400 years. It is the world's oldest standing segmental arch bridge, a title that speaks not just to age, but to a radical leap in engineering thought. While Roman bridges relied on the classic, powerful semicircle, the builders of Jeju chose a different path, a shallow, graceful arc that kisses the water. This segmental arch was a masterstroke of optimization. By flattening the curve, they dramatically reduced the amount of stone needed, and more importantly, the bridge's overall weight and the outward thrust on its abutments. This made it stronger, not weaker, by creating a structure that worked with gravity in a more efficient, balanced way. But the genius does not stop at the arch's shape. Look at the sides of the bridge and you see a series of open spandrels, deliberate holes piercing the masonry above the arch. These were not decorative. They served a brilliant dual purpose. First, they lightened the bridge's superstructure even further, removing dead weight. Second, and most critically, they acted as pressure relief valves during floods. When the river swelled, the water could rush through these openings, reducing the immense lateral force pushing against the bridge's sides. This was hydrodynamic thinking built directly into the form. The construction itself was a puzzle of perfection. The entire bridge is assembled from interlocking limestone blocks, fitted together with such precision that no mortar was needed. The joints are dovetailed, and iron cramps connect keystones, creating a monolithic, flexible unit that could shift slightly under load or thermal expansion without cracking apart. It is a self-stabilizing stone tapestry. The foresight embedded in every detail is humbling. The wide, gently cambered deck allowed for cart traffic, the ornate railings offered protection, and even the stone surfaces were engraved with subtle patterns to improve traction in the rain. This bridge was not an isolated marvel. It was the product of a sophisticated engineering tradition that understood materials, mechanics, and the environment as a single, interconnected system. It asks a question that resonates deeply with modern sustainable design. What does it mean to build for permanence? The Jeju Bridge answers that true endurance comes not from overwhelming nature with mass, but from elegant efficiency, from a design so intelligent that it accommodates the very forces that seek to destroy it. It is a lesson in listening to a river and in crafting a stone reply that echoes for millennia. A stone bridge withstands the river's force, but a hillside must hold the soil itself. Across the steep slopes of the Andes and the rugged highlands of Scotland, farmers and builders confronted a universal challenge: how to cultivate land that wanted to slide away. Their answer was a patient art of balance: the dry stone wall. Built entirely without mortar, these terraces and retaining walls are a quiet conversation between human need and geological reality. The technique is deceptively simple, yet it demands a profound, tactile wisdom. Each stone is chosen not just for size, but for its unique shape. The builder, working with hands and eyes alone, turns each piece, testing its fit, seeking the natural lock where its contours nestle perfectly against its neighbors. The wall grows not as a solid mass, but as an interlocking three-dimensional puzzle, held together by gravity and friction. This very lack of mortar is the source of its genius. Water from rain or melting snow can seep freely through the countless tiny gaps, draining away without building up pressure behind the wall that would cause it to burst. When the ground freezes and heaves in winter, the wall can flex minutely, the stones shifting just enough to accommodate the movement before settling back into place as the thaw comes. A well-built dry stone structure is not static. It is a dynamic, living part of the hillside. For the Inca, these terraces, or Andeans, transformed sheer mountain faces into fertile gardens. They created microclimates, captured water, and prevented the precious, thin topsoil from washing down into the valleys below. In Scotland, crofters used the same method to clear fields from rocky ground, creating pockets of arable land and livestock enclosures that have endured for centuries. This was engineering stripped to its essence. It required no imported materials, no complex tools, only a deep, localized knowledge of the available stone and the water flow of that specific slope. Each wall was a custom solution, a direct response to the land's own language. The legacy of this practice is a testament to sustainable land management long before the term existed. It represents a philosophy of working with the landscape rather than flattening it, of building resilience through intelligent adaptation. In our modern era of large-scale, machine-driven agriculture and engineered retaining walls, the dry stone terrace poses a gentle but powerful question. What solutions for erosion control and sustainable food production might we be overlooking in our pursuit of high-tech interventions? This ancient method reminds us that sometimes the most enduring stability comes not from binding things rigidly together, but from understanding how to let them move, drain, and settle in harmony. It is a reminder that the deepest engineering often begins with listening to the land and learning to build with the logic it provides. A dry stone wall holds a hillside, but a civilization must hold an entire season of rain. In the dry, seasonal heart of ancient Sri Lanka, engineers confronted a paradox: how to build a thriving, rice-fed society in a landscape of long, harsh droughts broken by intense monsoon deluges. Their answer was not a single dam, but a living, breathing hydrological organism, a cascading network of reservoirs known as tanks. This was systemic thinking carved into the earth on a regional scale, a 2,000-year-old lesson in sustainable abundance. The system functioned with the elegance of a natural watershed, but one guided by profound human foresight. Large primary reservoirs were built by damming rivers in the highlands to capture the furious monsoon rains. From these giants, water was released through carefully engineered canals into a descending staircase of smaller, interconnected tanks that dotted the plains below. Each tank in the cascade had a specific purpose, from irrigation and drinking water to replenishing groundwater and supporting biodiversity. The true genius lay in the control mechanisms. At the heart of each tank's bund or earthen dam was the Bisokatuwa, a unique sluice gate constructed from stone and timber. This wasn't a simple hole. It was a precision valve, often a tiered tower with internal conduits that could regulate water outflow with remarkable accuracy, preventing erosion and allowing farmers downstream to receive a measured, reliable flow throughout the growing season. Just as vital were the silt traps, cleverly designed settling ponds placed at canal inlets. These captured sediment before it could choke the reservoirs, extending their lifespan for centuries and providing nutrient-rich silt that could be recycled onto fields. This entire system was a dialogue with time and nature. It transformed the destructive force of the monsoon into a managed resource, storing life in artificial lakes and metering it out across the dry months. It supported a dense population and a sophisticated civilization like the Anuradhapura kingdom, all while maintaining ecological balance. The forests surrounding the tanks were protected as catchment areas, understanding that the health of the watershed was inseparable from the health of the society. In our modern era, where water management often means massive, single-purpose dams and energy-intensive pumping, the ancient tank cascade poses a quiet, revolutionary question. What if the solution to water scarcity isn't found in ever larger, centralized concrete monuments, but in reviving the wisdom of distributed, nature-integrated systems? These Sri Lankan reservoirs were not imposed upon the landscape. They were a collaboration with it, a testament to the fact that the highest form of engineering mastery is not to conquer an environment, but to learn its rhythms so deeply that you can compose a symphony of survival within it for generations. The legacy of these 25 methods is not a collection of curiosities, but a single, resonant lesson. Ancient mastery was never defined by the complexity of the tool, but by the depth of the understanding behind it. These builders possessed an advanced knowledge that we, in our rush for technological solutions, often overlook. It was a profound intimacy with materials, a patient, empirical grasp of physics learned through hands and eyes, and a philosophy of harmonious integration with the environment. They worked with stone, not against it, with water, not in spite of it, with the forces of wind and earth, not in blind opposition to them. They were scientists conducting long-term experiments, artists sculpting with function, and ecologists managing watersheds, all long before those specialized roles were ever named. This challenges the comforting, linear story we often tell about human progress, the idea that we are always moving forward toward greater and greater sophistication. Their work suggests that sophistication is not a single destination, but a landscape with many peaks. A Roman arch, a Persian Qanat, and a Maya temple that sings each represent a different kind of high achievement, all reached through observant curiosity and pragmatic innovation. The true foundation of their engineering genius was not a secret formula or a lost power source, but something far more accessible and yet profoundly difficult to sustain, a willingness to listen closely to the world and to apply what was learned with patience and immense scale. In the silent precision of a stone joint, in the gentle slope of a buried canal, in the calculated flex of a wooden pagoda, we find a forgotten language of resilience. It is a language that speaks not of domination, but of dialogue, offering timeless answers to the enduring questions of how to build, how to live, and how to create things that are meant to last. From the self-healing concrete of Rome to the seismic dances of Inca walls, these 25 ancient engineering methods reveal a forgotten world of construction mastery that continues to astonish and inspire. They are not merely historical footnotes, but a vibrant testament to a different kind of genius, one rooted in profound observation and a deep, collaborative relationship with the natural world. These builders did not see materials as inert substances to be dominated, but as partners in a dialogue. They listened to the whispers of stone, the logic of water, and the rhythm of the earth, and their structures were the eloquent replies. This mastery challenges the very narrative of progress, suggesting that sophistication is not a linear path toward greater complexity, but a landscape of diverse peaks, each reached through a unique harmony of mind, material, and environment. They remind us that human ingenuity, when deeply connected in this way, can achieve the seemingly impossible, crafting legacies that endure for millennia. As we face our own pressing global challenges in sustainability, resilience, and resource management, we stand at a crossroads. The instinct is to look forward, to seek salvation in ever more advanced and energy-intensive technologies. But perhaps the most revolutionary answers lie not only in looking ahead, but in glancing back, in rediscovering the profound wisdom locked in the stones of the past. The Roman aqueduct asks us how to move water with gravity, not grids. The Persian Qanat shows how to hide a river from the sun. The Sri Lankan tank cascade demonstrates how to turn a single monsoon into a year-round symphony of abundance. These are not outdated ideas, they are timeless principles of efficiency and integration. Let this journey be a call to look at ancient wonders with new eyes, not as mysterious relics shrouded in legend, but as active textbooks written in architecture, geology, and physics. They are blueprints for a different kind of future, one built on the foundational principles of patience, observation, and harmony. If this exploration of forgotten mastery resonated with you, please subscribe for more deep dives into the mysteries woven through our history. And we would love to hear your thoughts. Which of these ancient techniques amazed you the most? Share your perspective in the comments below.